I'm going to start by talking about the types of data analysis questions. Not all data analyses are created equal. Each data analysis might address a slightly different question and require slightly different data types to be able to answer that question. I've categorized the types of data analysis questions into these 6 categories: descriptive, exploratory, inferential, predictive, causal, and mechanistic. They're ordered approximately in the level of difficulty it is to use real data to answer this type of question. I'll start off with descriptive. Descriptive is exactly what it sounds like. The goal is just to describe a set of data. This is the first kind of data analysis that was performed, and it's been going on for a long time. It's commonly applied to data from census, for example, the US Census. Here, the description and interpretation are different steps. While the goal originally might just be to describe the dataset, eventually that description might be used to make certain decisions. Descriptions can usually not be generalized without additional statistical modeling or used to make predictions about new sets of data without additional predictive modeling. So here's an example of a descriptive analysis. This is the website of the 2010 United States Census. The goal here was simply to enumerate all of the United States citizens, then gather some very specific information about those citizens, and use that information to apportion representation in the United States Congress. The goal is not to infer anything about a greater population or to perform any kind of prediction, it's simply to describe the population. Another example is the Google Books Ngram Viewer. The Ngram Viewer shows the relative frequency of particular terms over time in books that have been indexed by Google. Again, the goal is not to infer anything about the frequency of these words or to make any predictions about the future. It's simply to describe the patterns of observed frequencies of particular words or phrases in books that have been indexed. The next kind of analysis is an exploratory analysis. Here the goal is to find relationships you didn't necessarily know about. It can be performed on a census dataset, but it can also be performed on a smaller sample. Exploratory models are good for discovering new connections. They're also useful for defining future studies. But exploratory analyses are almost never the final say. The goal is to explore, not to necessarily define the relationships that you're finding. Exploratory analyses alone should not be used for generalizing a particular relationship to a new population or for predicting. You might have heard the phrase, correlation does not imply causation. It's particularly appropriate in exploratory data analyses, where you might see a particular relationship and think that you've discovered a new relationship between variables, but before you generalize that relationship or try to predict with that relationship, you should perform further statistical modeling. Here's an example of an exploratory analysis. In this analysis, fMRI was used to scan the brains of individuals who were performing improvised rap. Individuals who were performing raps that had been written out as a script had different areas of the brain that were active than people who were performing improvisation. In advance, people didn't know which part of the brain to look for this particular activation during improvisation. After this particular analysis, it wasn't explicitly concretely confirmed that those regions of the brains were the regions that contributed to being able to perform improvisation or any other creative task. But it did explore the activation in the brain during this particular process and give ideas for follow-up studies. Another example of exploratory analysis is the Sloan Digital Sky Survey. This is a survey of the night sky that's taken with a variety of different kinds of telescopes that collect data every night and store that data in a database that's accessible to the general public. You can look through that data to try to discover new stars or discover new supernovae. But regardless of what you do, the goal is simply to explore and to find new relationships. Confirmation would then need to be performed by focusing on that particular region in the sky and understanding the exact physical relationships and the objects that are moving there. The next kind of analysis is an inferential analysis. Here the goal is to use a relatively small sample of data to say something about a much bigger population. Inference is the most common goal of statistical models, and it's the main target of instruction in most statistical classes. Inference involves both estimating the quantity that you care about for a population based on a small sample and being able to quantify the uncertainty that you have about that estimate. Inference depends heavily both on the population that you care about and the way that you've sampled that population. Here's an example of an inferential analysis. Here, the authors looked at the effect of air pollution control on life expectancy in 545 U.S. counties for a period from 2000 to 2007. This is a relatively small fraction of the U.S. counties, and the goal was to be able to infer from this particular sample the relationship between life expectancy and air pollution so that individuals in other counties, so we would have an idea about the relationship in individuals in other counties as well. The next kind of analysis is a predictive analysis. Here the goal is to use the data on some objects to predict values for a new object. Something important to remember is that if X predicts Y, it does not mean that X causes Y. In other words, just because I can predict Y from X doesn't mean that if I change X, the values of Y will necessarily change in a specific, concrete way. Accurate prediction depends heavily on measuring the right variables. Trying to predict without the right variables will often lead to very low prediction accuracy. Although there are better and worse prediction models, more data and a simple model tends to work very, very well. This is a link to a presentation called The Unreasonable Effectiveness of Data that shows that a very simple model with a lot of data can end up having a very high prediction accuracy. However, prediction is often very hard, and especially about the future. Here's a list of references for people that have said this over time. It's a long list. Here's an example of a predictive analysis that you might have heard about. 538 is a blog that with the goal of predicting the outcome of elections in the United States. Here's an example of the predictions of the number of electoral votes that Barack Obama and Mitt Romney were likely to get in the election of 2012. It also shows the prediction of the number of electoral votes predicted at each particular day. At the end of the day, this prediction was actually a very good one, where all of the states were accurately called by the forecast of 538. Another example of a predictive analysis is this one. This is an example where a company, Target, is intending to predict who is pregnant based on their purchase patterns. So they use the receipts that a particular person has using their Target card to predict whether they're pregnant or not. This is important for advertising purposes. In fact, in this particular story, Target was so good at predicting who was going to be pregnant that they sent mailings for advertising a particular set of pregnancy-related products to a teen girl whose father did not know that she was pregnant. This, of course, led to some uncomfortable conversations. The next kind of analysis is causal analysis. Here the goal is to find out what happens to one variable when you actually force another variable to change. To understand causal relationships, we usually require a randomized study. There are approaches to inferring causation in non-randomized studies, but they are complicated and sensitive to assumptions. Causal relationships are usually identified as average effects, but not apply to every individual. In particular, if I've identified a treatment as being effective for a particular population, if I give that treatment to an individual person, it's not clear that their particular case will be improved. Causal models are usually the gold standard for data analysis, as doing much more than this without a large amount of outside knowledge is very difficult to do. Here's an example of a recent causal analysis that appeared in the New England Journal of Medicine. It concerns a particular set of patients who have a particular infection, and the goal is to see if a transplant of feces will be able to cure that particular infection. In this study, a certain number of individuals were randomized to receive the fecal transplant, while another set of individuals was randomized not to receive the transplant. At the end of the day, the transplant led to a reduction in the infection, and so we were able to infer a causal relationship between these two variables. This was only possible because individuals were randomized to receive the treatment or not. The next type of statistical analysis is mechanistic models. Here, the goal is to understand the exact changes in variables that lead to changes in other variables for individual objects or people. What I mean by this is, if we change the value of a particular variable for one object, then another variable for that object will change in a very predictable way. This is incredibly hard to infer, except in very simple situations. It's usually modeled by a deterministic set of equations, and they often come from physical or engineering sciences rather than biological sciences or social sciences, where it's much harder to understand the exact relationships between variables. Generally, the random component of the data is measurement error in these cases. And if the equations are known but the parameters are not, we can infer the parameters with data analysis. Here's an example of a mechanistic analysis. It concerns the mechanistic empirical pavement design. In this case, there is a mechanistic model for the way that pavement behaves under certain conditions, but the parameters are unknown, and they can be inferred with empirical studies. Again, this is a particular engineering problem where the mechanistic properties are well understood. In general, it might not be so easy to perform this type of analysis.